My talk, or my poster, is about estimating communication subspaces with low-rank RNNs. It's supposed to be a follow-up of Joao's talk. Maybe then he will give a follow-up on the same work tomorrow. Yeah, exactly. So we're interested in finding structure in across-region interactions and have some good insight already from this influential paper named Cortical Areas Interact Through a Communication Subspace, where they have simultaneous recordings from two brain regions, namely V1 and V2, and then reduce or subtract the stimulus signal from the neuronal traces and study the trial variability or noise correlation. They then apply a reduced rank regression and find that V1 communicates with V2 through a lower dimensional subspace. We would now like to expand this paradigm and study signal correlation or condition variability with a task, we just call it the MANTE task, a contextual decision-making task. And we also have parallel recordings of 6 brain regions. This makes it a little more challenging, so we're using multi-region lowering RNNs. I will introduce them now. So let's start with a vanilla RNN. In our case, we're mapping neurons from the data and the model 1-to-1, and then match the traces through backpropagation and minimizing our loss function, mean squared our loss function. But we also penalize the rank, and how we're doing that is, suppose you have a J matrix connecting all neurons from all regions with each other. Now, each particular connection of an area is, like here, A and C, from A to C, is parameterized by a low-rank matrix consisting of the outer products of the singular vectors M and N, multiplied with their singular values S. Now make use of those singular values by summing them up and penalizing them, adding them to the loss function, multiplying them also with lambda that we find through a grid search. Now, after training and cross-validation, we can plot the distribution over singular values, and we find that indeed most of them got pushed close to 0. So that's good. We can also now take a look at each particular connection between the areas. Here we plot the dimensionality of across and within communication of the particular areas. We use the p ratio of the singular values of those low-rank matrices and see that indeed for V4 and parietal cortex, they share they have low-dimensional communication subspaces. The other areas not really, might be due to that we focus on signal and not noise. But also, very interestingly, is that we see a compression of signal towards frontal areas, which might hint to a more abstract representation of our task in the frontal areas. That's also along the lines with the paper, the lower one, in human fMRI, where they see a compression of signal from sensory to association areas. But even cooler now, and that's supposed to be Joao's talk, or also my poster, we now have a generative model of 6 brain regions interacting with each other, and so we can do in silico experiments and do some quasi-causal inferences of their connections and the impact of those. Yes, so if you're interested in this, visit my poster tomorrow, or attend his talk tomorrow, do both. And since Joao couldn't promote this, I want to give a quick shout out to Caleb, who is having a poster today. He's also using low-rank RNNs, but fitting single trials of neuropixel and neuromodulators photometry to investigate how neuromodulators shape network dynamics. Thank you.